Good morning, everybody. I am really quickly going to go over what I really wanted you guys to focus on from the reading. For those of us that didn't have the textbook questions, I scanned them, but a lot of the diagrams did not show up well. So I also wanted to make sure that we're looking at that. So previously, we've been talking very large scale. And covering a lot of the fundamental properties of meteorology. As we go and broaden our knowledge, we're also going to be applying different concepts to different scales of motion, different scales of atmospheric phenomenon. So when we think about different scales, we have, the micro scale, the very, very small scale, tiny little turbulence and flow. We have the mesoscale. You can almost think about the mesoscale as, if you went outside as far as you can see, would cover about the mesoscale. And then, of course, we have the synoptic scale, which really covers extremely large systems that can span the entire country. This diagram here just really kind of outlines not only the scale and the size, but the scale and the time frame for how long the phenomena at these scales really last. So, on the micro scale, you're talking about interactions that take place over a space of a few meters, but also whatever those interactions are, they only tend to last for a few seconds or minutes. On the other hand, when you talk about mesoscale thunderstorms and things like that, well, yeah, they can go hours to days. And then the larger spatial scale, you're also looking at a larger time scale. So on the global scale, you're looking at systems that we can follow for weeks at a time. So first we're going to talk about friction just briefly. Friction is not exactly what you would think of it as, the same kind of friction that we might talk about in a physics class, or the friction of your brakes. But the fact is that when air is moving slower, air moving at different speeds, when faster air interacts with that air, they will kind of mix and they'll kind of share. So what we're looking at here are basically two different temperature profiles. One is a temperature profile that you might see when the air is fairly stable. And one thing that you can kind of see is that you don't get a lot of mixing. You can get a lot of variation there because we're not getting any kind of friction. But if we have lots of wind speed and you're getting a lot of interaction between your upper air and lower air, well, then we get a lot of mixing to happen. So an unstable air also produces a lot of mixing. So one impact of air mixing at different speeds and properties is that you do see these little swirly patterns, which we refer to as eddies. You have to keep in mind that we can summarize things on a bigger scale, but the atmosphere needs to stay continuous. And eddies are kind of the things that show up to kind of fill in the gaps when we have gaps in the atmosphere, or things changing from one place to another. You might get those little swirly eddies to kind of balance that out. So let's say, for example, we have air moving over this mountain. All right, well, that air, as it moves over, can kind of create a gap here And so there's going to be a vacuum, there's going to be low pressure on the backside of this mountain wave, and so then we get some air that's going to kind of swirl back in and fill that low pressure. And then as that wave, kind of that disturbance goes through, and we get this air moving, you can get these kind of swirling eddies below a crest that swirl around. Another example is on the backside of a mountain or hill. Even if we're looking at westward facing winds here, the low pressure on this backside is going to actually swirl back around, and so you might experience while these cars are you'll experience a change in the wind direction as you go down this road. Some other impacts of friction are to, again, it slows down the airspeed. So where you see these, if you've ever been out in the plains, you see these windbreaks that are trying to slow down the winds as they sweep across these plains where there's really low friction. And you can tell that it's working because as the air slows down, it can't suspend as much snow particles and stuff, and so when it slows down, some of the snow falls out and we get these little mounds behind our windbreaks. This is particularly helpful in agriculture because wind is a form of erosion. It takes away good soil if you have a field that you're growing your crops on. So a shelter belt is a row of trees, something that will greatly reduce the wind speed, and then that reduces the amount of erosion that you're going to see in your farms. We see turbulent atmospheric eddies, and in the ocean, any fluid really, that form with the surface of the ocean. Now, friction is one of those forces affecting our winds, and so the other thing that we can see, a friction effect, is that when we have nice smooth surfaces, there's less friction, and that allows our wind speeds to be greater. And that also changes that kind of balance between the pressure gradient force and the geostrophic force, the pressure gradient force and the Coriolis force, giving us that more geostrophic wind. We want to talk about how these systems can form on a smaller scale that give us, rising air, that we see that is similar to what we look at with instability. Rising air gives us cooling, condensation, and possibly even precipitation. So if we think about a lake with nice smooth air, less friction, that allows our air to go faster, right? So it's kind of like if traffic lets up and the speed limit increases, cars are going to get further apart from each other. Well, that means we have diverging air over on this side before, as the air starts to speed up. And then when the friction comes back on the other side of the lake, you get convergence, and that sends, air up. If I have divergence below, that's going to give me sinking air. And if I have convergence below, I'm going to have rising air. Because again, the atmosphere is continuous. That wind has to have somewhere to go. So we can see that with friction. I really want to focus on what happens in a thermal system because we can see these in lots of places. So a thermal system is a circulation that we see due to a difference in horizontal temperatures, right? So we talked about this before. When the temperature is higher, the column of air is going to be bigger, right? It's going to expand. And so while the pressure might be the same, or at least start out the same on the surface, whether it's, cold and warm, The pressure up aloft is going to be different because the colder air is going to change pressure rapidly with height. The warm air is not going to change pressure rapidly with height. So we see at the altitude, I have high pressure and low pressure, high pressure above the warm, low pressure above the cold, but that's at altitude. But that does initiate some sort of circulation. So now I have air moving from high to low. And that means that if air is moving from high to low, that means that this column no longer has as much air in it. Right? Air is leaving this column. So then our surface pressure actually starts to drop. And as air is entering this column, its surface pressure begins to increase. And so then we get the opposite. So one thing I want you to really focus on here is that high and low pressure, we're always comparing in a horizontal sense because we know that pressure always decreases with height. The pressure up here is always going to be lower than the pressure up down here, right? If you go up in a column, the pressure always decreases. But we want to compare horizontally to say what direction the wind is going. So that's an important thing. And then you also need to make sure that you can distinguish between, right, an upper level low and a lower level low, right? Because a surface low is usually associated with warmer temperatures. A surface high is colder temperatures. But because of that warmer air and the thicker column, an upper level high pressure actually could correspond more to a warmer temperature at the surface. And so when we think about what these, surfaces are going to look like, we can kind of get that 3D look where we can say, all right, here's the middle of our atmosphere, and when I have this, thermal high, that's actually because I have cold air, right? So high pressure comes at the surface comes from cold air, and so I'm going to have higher pressure at the bottom, lower pressure at the top. For our thermal low, where it's warmer, I end up getting lower pressure at the bottom and higher pressure at altitude. Where we see this frequently and on a smaller scale all the time is the idea of a sea breeze and a land breeze. So the water is always slow to change its temperature. There's a lot of it, and water has a very high specific heat capacity. So in the day when it's really, really hot, the land heats up and gets hotter than the water, and I have that cold high pressure over the water and the warm low pressure on the surface of the land, and that gives me this circulation, right? It is a thermal circulation, and we call this a sea breeze, just like we do any of our wind directions, because it's coming from the sea. On the other hand, at night, when the sun goes away, the land cools off faster than the water does, and so the land can actually get colder as well, and that gives us a land breeze. And so this is a very common circulation that you see. So that was really the main aspects that I wanted you to get from this. I'm trying to keep this fairly short, but we can kind of see, why do we always get these late afternoon thunderstorms in Florida? Well, it's because they have a double sea breeze coming from both sides every day that create a lot of upward moving air. And so, yes, they get late afternoon thunderstorms, and if, there's not some other system coming through, a lot of times it'll, clear out by the nighttime, because then that system, kind of reverses itself, and now instead of rising air over land, I have sinking air over land, which we know can be very stable. All right, well, I hope you guys enjoy this. Have a good day, and stay safe.